So we now want to test this hypothesis that each photon delivers also a discrete amount of momentum in addition to the discrete amount of energy coming in precisely this amount. So the classic test of this was a very famous experiment due to Compton. So this is the Compton scattering experiment. And this was dated to 1923. And it's really a beautiful confirmation of this result. So the way the experiment is set up is, again, it's a scattering experiment. We're doing a lot of these, right? So you're going to have some kind of source. Now this source is actually a source of gamma rays. Gamma rays are very high frequency light waves that have a lot of energy. They're higher frequency actually than X-rays. So I will denote them by a wavy line. So remember, this is electromagnetic energy that we're talking about. And this source then is going to have some initial frequency that it has, a well-defined frequency. You can find sources that do give you a well-defined frequency. For now, I will call that frequency nu naught, like so. Now, the next piece of the experiment is that you direct that towards some kind of target. And that target is going to contain, usually it's a metal target, it's going to contain many electrons in here that we can then interact with. And our picture is, okay, these photons are going to come in, they're going to deliver some energy and momentum. That's going to shoot electrons out in one direction. And then photons will come out maybe in some other direction. At least that's our hypothesis. And we can look at then as a function of angle theta. We can put a detector here. And detect any photons that come out. And in particular, we can measure the frequency then of any photons that we see coming out. And I'll call the outgoing frequency here nu that we would measure. So then the results that we find are very intriguing. So the results will look something like this. What we would do then is we're going to sit at a particular fixed angle. Here, theta will be fixed. And I'm going to plot then at that angle the brightness of the radiation that's being received by my detector, and I'm going to look at that as a function of frequency, nu. And as I do that, I find some interesting results. The first thing I notice is that there's nothing at very high frequencies, and then I begin to build up, and I see a very nice peak, and this peak, it turns out, is centered right at the frequency of the incoming light. And I should say that that is precisely what we would expect from classical physics. Remember here the classical physics view, and Naomi will be looking at this a bit with you in section. But the classical physics view is as follows, right? I've got this continuous electromagnetic field that's coming in, where the electric field is, say, oscillating up and down. There are electrons in here. They move up and down with that electric field, and they then oscillate at a frequency. And they, of course, move in sync with the incoming electric field. So when we drive a particle at a given frequency, it responds by oscillating at exactly that same frequency. The next stage is once they are oscillating, this is the classical picture from this incoming continuous E&M wave, they're oscillating up and down. As they oscillate up and down, the electric field that they create has a vertical component then that is moving up and down. When I look at it from far away, it's moving up and down as the electron moves up and down. When the electron is up, right, the electric field, well, you might think it would be down, but it's negatively charged, so it's up too. And so the electric field then begins to oscillate up and down in sync with my electrons. And as that electric field oscillates up and down, that eventually becomes this light wave when I look at it far away. The frequency of the up and down movements of the electric field, of course, because they are being generated by the up and down movements of my charge, occur at the same frequency as the up and down movements of these electrons. And because, as we had said earlier, these electrons are moving up and down with the same frequency as the incoming radiation, we would expect the frequency of the outgoing radiation nu to actually exactly match the energy of the incoming radiation nu naught. So that's why this is sometimes called the classical peak. This is what we would have expected. But as you continue then decreasing the frequency, right, we see something very interesting. We see a secondary peak at some other frequency, which I will call here nu prime. At a lower frequency, in fact. Now that actually is more what we are expecting from our quantum picture. Because remember, the idea for our quantum picture is that my photon is coming in here with some energy and some momentum. So when it interacts with one of these electrons, the electron then is going to pick up that momentum that is delivered, right, from this photon. And because he picks up that momentum, the remaining photon that's left over, right, that moves outward, is going to have less energy because some kinetic energy now will be carried away by my electron. So I expect the outgoing photons to have lower energy, and because energy is directly proportional to frequency, E equals h nu, then I expect that the outgoing frequency after such a quantum event should be lower because the energy that's left has been reduced by the energy the electron carried away. So I should expect a lower frequency here like this. So right now, the result looks very consistent with our quantum picture. But what we really need to do is to carry out a detailed quantitative analysis so that we can actually verify that these measured shifted frequencies come precisely in the form we would expect if we assume our hypothesis for the momentum carried by the electron.